We now turn to more general second order elliptic operators. So omega as usual, bounded open set, bounded domain as I also call it, and gamma equals the boundary. Okay, so let Aij belong to C1 of omega bar for all 1 less than equal to ij less than equal to n, and such that for all x in omega and for all xi equal to xi1 xn in Rn, we have sigma ij equal to 1 to n aij of x xi xj is greater or equal to alpha times mod xi square. Okay, and where alpha is strictly greater than 0, is a constant independent of x and xi. Okay, so then you consider the following differential operator: minus sigma ij equal to 1 to n d by dxi of aij d by dxj plus a naught. Okay, so this is called a second order elliptic operator, uniformly elliptic in divergence form. The way you've written, usually a second order operator would have second derivatives, first derivatives, and a lower order term, zero order term. Here the second derivatives and first derivative have been combined in a special way, and therefore this is called the divergence form of the operator. Okay, so and we now look for find u such that, so minus sigma ij equals 1 to n d by dxi aij du by dxj plus a naught u equal to f in omega and u equal to 0 on d omega, okay, which is on gamma. So we assume now that f is given in L2 of omega, and then again, so now if I multiply by phi, so be phi in d omega, multiply and integrate by parts, and therefore this is where the d by dxj form will come into play. So you will get integral on omega sigma ij equals 1 to n aij du by dxj d phi by dxj dx plus integral on omega a naught ub dx equals integral on omega f of x, f, this is phi, okay, f phi dx. Okay, so if uv belong to, so now everything is continuous as far as h10 is concerned, phi is dense there, and therefore we get for all v, so you get that, so find u in h10 of omega, h1 so that all these integrals make sense, and 0 because it's in vanishes on the boundary, okay, such that you have auv equals fv where auv equals integral on omega sigma ij equals 1 to n aij du by dxj dv by dxi dx plus a naught integral on omega a naught uv dx. Okay, so this is the so we call this the weak formulation. So the weak formulation, you always have to mention three things: what is the vector space, what is the bilinear form, what is the linear form. So the linear form is integral fv dx on omega, f is in L2. Bilinear form is given by this expression here auv, and the vector space of course is h10 of omega. So that specifies. So this is called the weak formulation of star. So star is the differential equation here with together with the boundary condition. Okay, so again one can check that if you have a weak formulation, then it satisfies differential equation in the sense of distributions, and of course the boundary condition is satisfied because we have put it in the space itself. And so we now have, if a naught is strictly positive in omega, then auv is h10 omega elliptic. That's easy to see because of the condition of the ellipticity condition. What is the ellipticity condition? Recall, this is called the ellipticity condition. So if you use this fact, and for xi I and xi j you substitute du by dxi dv by du by dxj, then you will get that au is greater than or equal to alpha times integral mod u square mod grad u square. Okay, so this is therefore by Lax-Milgram there exists a unique weak solution. And you can go back and forth. As I said, you can, if it's a classical solution, then you can show it gives you a weak solution. If it's a weak solution which is sufficiently smooth, then you get a classical solution. So in addition, from the abstract theorems we have proved, in addition, if A is symmetric, that is Aij equals Aji for all ij, then A is symmetric and U minimizes J over H10 omega, where JV equals 1/2 of AVB, that is integral over omega sigma ij equals 1 to n aij dv by dxj dv by dxi dx plus integral on omega a naught v square dx minus integral on omega fv dx. More generally, we can consider the following. Aij satisfies ellipticity condition. Okay, so I also want to show for weak formulation to make sense, enough to assume Aij, A naught are all in L infinity of omega. That's enough to make the integrals meaningful. So you can always suppose a weak solution, and then regularity theorem, if you can prove using extra properties of the Aij, A naught and of the domain smoothness, etc., then one can show that examine the question whether a weak solution is a classical solution or not. Okay, so weak solutions are what we will generally look for, and numerical calculations will be attempting to approximate the weak solutions only, and therefore the classical solution is a curiosity. If you have it, it's fine, otherwise it still doesn't matter. Okay. Okay, so now you consider you have minus sigma ij equals 1 to n d by dxi aij du by dxj plus sigma I equals 1 to n ai du by dxi plus a naught u equal to f in omega and u equal to 0 on d omega. So again aij satisfy ellipticity and ai are all in C of omega bar. So again we will see in a moment that we do not need so much, we will just see that everything is L infinity. Okay, so weak solution of this problem is find u in h10 of omega, so that's the vector space. Now we have to specify that auv equals integral on omega sigma ij equals 1 to n aij du by dxj dv by dxi dx plus sigma integral on omega sigma I equals 1 to n ai du by dxi v dx plus integral omega a naught uv dx equals integral omega fv dx for every v in h10 of omega. So once again you can check that this will satisfy the differential equation in the sense of distributions, and we have imposed the boundary condition automatically, and therefore this is what we call a weak solution of the problem. And in this case again enough to assume aij, ai, a naught are all in L infinity of omega. Then this makes sense, and therefore we can talk of weak solutions of this differential operator. Now the bilinear form is not symmetric. Not symmetric in general. If it is h10 omega elliptic, then we can use Lax-Milgram to prove the existence of a unique solution. But this may not happen. Okay, so therefore we have the following theorem. So omega in Rn bounded open set, aij in L infinity of omega satisfying ellipticity condition, ai a naught also in L infinity of omega, and f is in L2 of omega. If f equal to 0, the set of solutions to double star. So let us call this equation. Okay, this is the weak formulation. Is a finite dimensional subspace of H10 omega. So let dimension equal to D. Then there exists a d-dimensional subspace of L2 of omega, capital F, such that double star has a solution if and only if F belongs to the orthogonal complement in L2 of capital F. So this is the orthogonal complement of F in L2 omega. So now, so we will prove this, and you will see how nicely functional analysis comes to our help in solving these problems. Okay, so choose lambda positive such that a naught of x plus lambda is greater or equal to gamma, which is strictly bigger than 0. Okay, so this can always be done because a naught is L infinity, so it is bounded. So if I add a sufficiently large constant, then it will be always strictly positive, and you can find a minimum value which is again strictly positive for all x in omega. Okay, so now let mod ai 0 infinity omega less than or equal to beta for all 0 less than or equal to I less than or equal to n. Now let v be arbitrary in H10 of omega. Then you look at AVV plus lambda integral on omega v square dx. Now because of the ellipticity AVV, so if you look at this expression here, AVV, the first term will be aij du by dxj du by dxi sigma ij, and that is greater or equal to alpha times mod u square d by dxi, okay, 1 omega, so du by dxi square, and therefore you have this is greater or equal to alpha times mod v square or 1 omega, then minus. So here you have ai's are all less than beta, and therefore if you do the Cauchy-Schwarz inequality here, you get mod u 1 omega mod v 0 omega, so u equals v again. So if you, and since you are going to get a lower bound, you put a minus sign, this is minus beta mod v 1 omega mod v 0 omega plus, then you have a naught v square plus lambda v square is also there, and that is greater or equal to gamma. Okay, so gamma mod v square 0 omega, and that is equal to alpha times mod v square 1 omega, and then we complete the squares for these two terms, and therefore you have gamma plus gamma power half mod v 0 omega minus beta by 2 gamma power minus half mod v 1 omega whole square. So if you take the square term, you have gamma mod v square 0 omega, which is already there, minus 2 beta, and then the gamma will get cancelled, so and the 2 will also get cancelled, beta times mod v 1 omega mod v 0 omega. So we have this thing, and then we have a cross term, second term, which is this one, so we have to subtract that, minus beta by 4 gamma times mod v square 1 omega. Beta square, sorry. So this is therefore greater than or equal to, so this square term is greater or equal to 0, we ignore it, alpha minus beta square by 4 gamma times mod v square 1 omega. So if we choose lambda large enough, implies gamma large, we can have alpha minus beta squared by 4 gamma greater or equal to 0, and so A plus lambda times is H10 omega elliptic. That is AUV plus lambda times integral omega UV. This bilinear form is H10 elliptic. So if f belongs to L2 of omega by Lax-Milgram, there exists a unique u in H10 of omega such that AUV plus lambda times integral uv on omega dx equals integral fv dx for every v in H10 omega. Then by the ellipticity we know that f mapping to u, which I am going to call g of f, is continuous by ellipticity. We already know that if you have AUV equals FV, and then we have seen that f going to u is a continuous mapping G, and it is 1 over the ellipticity constant is the norm of that operator. Okay. Now, so you have from L2 of omega into H10 of omega, you have f here going to u, and now this will go back to u, so this is inclusion in L2 of omega. And we know this inclusion is compact by relic. By the relic Kontrasov theorem, H10 omega into L2 of omega is elliptic because omega is a bounded open set, and consequently composition of compact mappings is compact, and therefore you have the G from L2 to omega, L2 omega into L2 of omega is compact. Now if U solution of double star, what is double star? It is a weak formulation of the equation here, which is this expression here, AUV is equal to this. Then if you add a lambda UV to both sides, then you get this thing. Then you get AUV plus lambda integral UV equals FV plus lambda integral UV. Okay. So this implies that U is the solution is G of F plus lambda U. So you put F plus lambda U equal to V, then you get lambda U equals lambda G F plus lambda U, and lambda U is what? Lambda U is V minus F. Okay. So you substitute all these things here in this equation, so you get V minus F equals lambda GV, or in other words V minus lambda GV equal to F. So if you can solve for V, you solve for U, because U is given by f V minus f by lambda. So U equals V minus f by lambda. So solving for U is same as solving for lambda. Okay, for V. But none, G is a compact self operator, and therefore its spectrum consists only of eigenvalues, non-zero spectrum. Okay, so either lambda inverse eigenvalue of G or not an eigenvalue of G, or lambda inverse is eigenvalue of G. So if lambda inverse is not eigenvalue, then I minus lambda G is invertible, implies there exists unique V for every f, implies there exists a unique U for every f. Okay, that is D equal to 0. The set of all solutions for which f equal to 0 is the 0 solution only, and therefore D equal to 0. If lambda inverse is an eigenvalue, then it has finite geometric multiplicity. Since G is compact. So if you have a compact space and you have a non-zero eigenvalue, then it is of course has to be finite, the null space, that is the space of eigenvectors, will be finite dimensional. Then by Fredholm alternative, V minus lambda GV equal to f has a solution if and only if f belongs to kernel of I minus lambda G star perp, because you know range of I minus lambda G is nothing but kernel of I minus lambda G star perp. Okay, so this is the standard theorem. This is called the Fredholm alternative, and therefore you have a dimension of kernel of I minus lambda G star is equal to dimension of kernel I minus lambda G, which is equal to D. Okay, and therefore you have this is our f, and you have, so f, small f must belong to capital F perp, only then you have a solution. So this proves that you have this proves that theorem. Okay, so we will continue with further examples later.